Okay, 5.4 logarithmic functions. A logarithmic is basically a question, and in my opinion it provides the answer to the following question: what exponent do I need to have with this base to equal a known value? So for example, if I said log 4 of 16, then the question I'm looking for is what exponent, so the answer is going to be the exponent, do I need to have with a base 4, so 4 is the base, to get the known value of 16. Okay, so again, what exponent do I need to stick on 4 to get 16? Well, so the answer is 4 to the second is 16. So that means that the log base 4 of 16 is going to give me 2. So an exponential expression, the answer to it is actually an exponent. So sorry, I said that wrong. A logarithmic expression, the answer to the logarithmic expression is the exponent that we're looking for. So logs are basically exponents. One reason that people came up with logs is to figure out how to undo something like this. So if you had to find the inverse of y equals 2 to the x, okay, then the first step is find. And then now how do you solve this for y? Okay, so how do I get the exponent y, and how do I get that exponent down? Well, a log 2 on both sides will bring that exponent down if we define a log as the inverse of an exponential expression. So the log 2 of y, somehow this just gives you the value y. So log 2 of x is the inverse of y equals 2 to the x. So here then is the definition of a logarithm. The logarithmic function to the base e, where a has to be larger than 0. So just like with exponentials, we can have negative bases. So here the base has to be larger than 0 as well. Is defined as y equals the log a of x if and only if x is a to the power of y. So the log function, the logarithmic function, is only defined based on having an exponential function that it's the inverse to. Okay, the domain of the logarithmic function is x needs to be larger than 0. And hopefully, if you think back to this domain here, for this one, the domain was all real numbers, right? But the range was what has a horizontal asymptote, and after that, it always stays above, and it does get really close when you have a negative exponent, but as soon as you have a pretty big exponent, it's super large. So the range was above 0 to infinity. Well, the range becomes the domain of the inverse. Okay, so let's practice a couple of these things. So if 4 squared is 16, then the log 4 of 16 is 2. If 2 to the 5th equals 32, then the log base 2 of 32 is 5. And then 10 to the 7th is 10 million, then the log base 10 of 10 million is 7. So if I'm giving you 3 to the 4th equals 81, then you should be able to write that the log base 3 of 81 equals 4. And on this one, the log base 7, because 7 is the base, of 1 divided by 343 is a negative 3. I guess I sort of answered that already up here. So what are the domain and the range of the exponential functions? So an exponential function, again, y to the power of a to the x, the domain was all real numbers, and the range was y needed to be larger than 0. So if they're inverse, then y to the log a of x, then the domain will have to be that x is larger than 0, because they're inverse, and then the range is all real numbers. Okay, one of the things that we're going to start with is just rewriting some stuff. So it says, for example, on these that we need to change each exponential expression to an equivalent expression involving a logarithm. Well, that's basically what we just did a moment ago. So the log base 5 of t equals 8. Keep in mind that the exponent is the answer to the log. Logarithm is usually abbreviated with log. So x negative 2 equals 12. So the log based x of 12 is a negative 2. The log based e of 10 is going to be x. And we'll learn, and I don't know if we'll do this lesson, but a log base e is usually written as the natural log natural. So this could also be written this way. And it means the same thing. Changing logarithmic statements to exponential statements then means the other way around. So keep in mind that this, the answer, is the exponent. So 2 to the power of y is 21. Or I think that's a z, so I'm going to say that's a z. So z to the power of 6 is equal to 12. Or 2 to the power of a is equal to 10. Sometimes you can find the actual value, and I usually do this by, well, some of these you will know from memory, but just put a variable over here and rewrite this as an exponential expression. So 3 to the power of x is 81. Well, 81 is 3 to the 4th, so that means that x has to be 4. Over here, 2 to the power of x is 1 over 8. Well, 2 cubed is 8, so I guess I need a negative 3 to make it 1 over 8. And then here we have one that's a little bit more difficult, I think. So on this one, we would write that the square root of 3 of x, or to the power of x, is 81. Then you sort of have to see that the square root of 3 could be written as a base 3, so that would make this a half x. And 81 is 3 to the 4th. We saw that a moment ago. So if a half x is 4, then x must equal 8. Okay. What does a logarithmic look like graphically? Well, let's look at 2 to the x, and we'll use that to create an inverse. And then that inverse will be the log base 2 of x. So here's 2 to the power of x. So in a negative 1, that would be a half. At 0, it would be 1. And at 1, it would be 2. So if I graph that one, then I should get 0, 1, 1, 2, and a negative 1, a half. So that looks a little bit like this. Wow. Let's try that again. Okay, keep in mind that this is an asymptote at y equals 0. So the inverse of that, which would be the log 2 of x, I should be able to just swap my x's and y's. So now I get a negative 1, 0, and 1 here, and then 2, 1, and a half go over here. So at 1 you should be at 0. At 2 you'll be at 1. And at a half will be at a negative 1. And you can see graphically that it does seem to mirror in the line y equals x. That's one thing you should know. And I also want to point out that if y equals 0 is an asymptote, then for the inverse, x equals 0 is an asymptote. Okay, so that is a picture of a logarithmic function, and it's the exponential function that it's tied to. What if the base is less than 1? So what if I first looked at 1/3 of x? So if you look at 1/3 to the power of x, then the table for that, I'll make my xy table over here. So let's see, at a -1 you would get your 3, at 0 you'd still be at 1, and at 1 you'd be 1/3. So all this flip-flops. Now that does mean that you get a little intersection right there, where both the x and the y are the same. So these do work. I struggle with these a little bit, to be honest with you, because I don't always graphically, I have trouble with inverses a little bit. So I have found that if I need to work on so this was the log 1/3 of x, that if you give me something that looks like this to graph, then I usually cheat. And what I mean with that is, we'll scoot for a minute down, so the log 1/3 of x is equal to y. I will actually just write it this way. Sorry, that's backwards. I will say that, well, that's the inverse to y to the third, or 1/3 to the y equals x. And then I'll use this stuff sort of to plug in values for even, and I'll just keep it this way. I'll plug in values for y that I know, so if I plug in 0, I know 1/3 to the 0, anything to the 0 power is 1. And if I plug in a 1 for y, I know I get 1/3. And if I plug in a -1 for y, I know I get my 3. So then I create my table sort of by using the exponential notation that goes with the log notation that we were given. Okay? Properties of logarithmic functions. So the domain is the set of all positive real numbers. The range is the set of all real numbers. So that's tied to that whole inverse thing with the exponential. The x-intercept is the graph except 1. Okay, so it goes through 1, 0, because anything to the power of 0 is 1. So the log of 1 is always 0. Vertical asymptote. Again, we have a horizontal asymptote for the exponential, so a vertical for the logarithmic function. Decreasing if a base is between 0 and 1, and increasing if the base is larger than 1. And then it contains sort of the points, and then the graph is smooth continuous with no corners or gaps. And that is because it's the inverse of the exponential with this, which is smooth and continuous, so this one will have to be smooth and continuous as well. Thank you.